Hello, Udine. My name is Gavin Stout. I'm the Powertrain Sound Quality Subject Matter Expert here at JAGUAR Land Rover. Absolutely gutted that I'm not there with you in Italy at the summit. However, as I am here, still here in sunny Gaydon in the UK, recording this for you. It's a pleasure to be able to give you an insight into how we do things and how we use the technology and the software here at Jaguar Land Rover and how it's evolved over the years since I've been here, which is essentially over the last almost 12 years. So without further ado, I'll just kick off the presentation. So quickly running through the presentation objectives. So I want to start off by running through the primary role of the FVS at JLR. I want to then move into the strategy for using the FVS within the early product life cycle, how we do that here. Then I'd like to run through a few examples of the model build process, or the early model build process, particularly focusing on battery electric vehicle application. And then finally, I just want to touch on a number of the key points or the key takeaways that we've had in terms of transitioning the FVS to becoming integral and really making it a turnkey tool to be used within the NVH development process. Okay, in terms of the primary role of the FVS then, so I want to start by talking through the two fundamental bookends, so it help frame the discussions later on. So we generally adopt two processes. So we have a benchmark model process and a source path to zero model process. So it may be familiar to you or not, depending on where you are in your own journey. So benchmark models are generally reserved for competitor model builds or for building a correlation model of their own vehicle with which the driver or target vehicle against. Now, a benchmark model will typically take between 3 and 4 days to instrument and measure, followed by, say, about 2 to 3 weeks to build the acoustic, the vibration, and performance model. Now, that can extend if you're running a multiple coherence decomposition. So if you're interested in breaking down the airborne and structure-borne road noise and wind noise. Now, that's compared to the source path receiver model, where, as I say, everything's built from the ground up in terms of your source strengths, your transfer paths, and building those into your customer level contributions. Now, the second model is, see, we're at a stage now where it can take between 2 days and 2 weeks to build, depending on the level of data that's available at the time. And then, as I say, working in this domain, so this is where we typically run through our evolution and the design maturation process for a given vehicle. And obviously there'll be iterative work that you do in terms of design improvements. So as I say, individual iterations can take between an hour to 24 hours, depending on the specific application. And then just to add, in this domain, so where you have an internal performance model which is built from measured performance on track, we also have a Simulink hookup, which allows us to use 1D developed vehicle models, which are run within our powertrain department. So the integration is, as I say, that we have in this domain is really quite powerful. So in terms of, I'll quickly touch on where we can use it. So again, this is what we use to highlight the statement, to highlight what the simulator is within the business. But in terms of where we use it, so confirmation and validation of NVH targets, whether we're looking at vehicle system and component level. It supports the customer level interaction with NVH data. So we're moving from an area where we, particularly in terms of early engineering, where we're all comparing two-dimensional data against targets, or looking at color maps versus actually getting to feel and really interact with the car. So the simulator provides a completely repeatable driving experience from subjectively from driver and objectively from driver to driver and on day to day. and allows for iterative comparison and validation of your design concepts, as I mentioned before. Also, instantaneous back-to-back assessments of vehicles, so having the ability to drive a competitor vehicle directly back-to-back with a developed vehicle is extremely powerful, not having to rely on acoustic memory. And actually, we find that the process of building the models gives you so much insight into the performance of the vehicle, to the fundamental NVH performance of the vehicle, which is I think is really important and key to the summit. It solves the problem of having no physical properties before your engineering stops. A quick run through the timeline, so I won't go into too much detail here. So this is essentially the journey of the software and hardware in the company. So early on, everything was built using the benchmark process, and any development would then be applied as filters in the mixer. Versus 2017 is when we first started to build our source path receiver models from the ground up, and installation of our FVS hardware actually happened 2018, up to where we are now, which is where we're now have the processes fully integrated, and now we're working in the BEV domains. So as I say, it's been a very, very interesting and fulfilling journey. At the bottom, just to highlight the evolution of the number of or the data sizes that we have to cope with, number of files, and also the build times. So you can see the build times extending up to when we first started running the source path receiver models to where we are now. So again, we're building models between, on average, it takes a week for a build. So vast improvements here. So where does FVS fit in the product lifecycle? So from a system engineering perspective, see, most of you should be aware of the system engineering V. So the initial validation of the targets down the left hand side, so customer down to component levels, and then the validation verification of those targets once you have physical properties around you. So moving this to a timeline. So you can see those data gateways at the top, which are the ellipses we saw before. Beneath that we have a digital series, so where the C loops supply the data that's required at the data gateways. Beneath that we have the system hardware and vehicle hardware provision. So this is where we first start to get information from test. So whether we're measuring our data from rigs or on actual vehicles or early vehicle prototypes. So the aim is for us to have simulator models and free driving simulations available at each of the data gateways to help us validate the engineering. So early on, where this is all about generating our targets and confirming that our targets are correct for the model and are correct for the customer. This is where we need to convert those fundamental engineering targets into data that can be consumed by the simulator. Moving forward, and once we're moving into our virtual loops, this is where we have to take data that's generated either in, for example, in FEA, SEA, MVS, all of your standard C tool sets. Again, we have to convert those into the data sets that the simulator can use. And finally, once we have our test data available, again, we have to translate those data sets. So we need to set up these translation routines all the way through the life cycle of the process to help us build our models. Now for some examples. So our first example is on our customer level target model. So this is where everything's built directly from the customer level targets. So breaking it down into your three key acoustic domains, wind masking, road masking, and powertrain content. So for each of these, we have a series of segment target objects which are created and managed through annual process. So again, if you have a D segment vehicle, or a vehicle which is assumed to have say D segment wind masking and road masking, it may have an E segment powertrain content which is carried over from in terms of its entitlement from a previous program. So the idea is that you would take the content for each of these areas and then build a free driving model for the target vehicle, which is then driven by your Simulink performance model. So at this point, this is really just getting initial validation that the customer experience is correct at a high level. So taking those customer level targets, we now look at starting to break down those customer level targets into the separate system targets. Currently, in terms of wind and masking and road masking, we don't have the integration set up in terms of breaking those down into source strengths and transfer functions. However, that's something we do have in terms of powertrain content. So our powertrain installation technical chapter within vehicle NVH, they create these quite concise and detailed target documents where the customer level contributions are broken down into airborne and structure-borne content, and each of those are then subsequently broken down further into source strength and transfer functions. So ATFs and radiated noise versus your structure-borne content where your NTFs broken down and powertrain forcing. Again, a Simulink performance model is then is used. Evolution from in terms of 1D performance of the car comes from the powertrain domain, and we build a free driving model. Now, the free driving model will then be driven by the key stakeholders, and then everything being correct and everyone being happy with the customer level performance of the vehicle, that gives us the green light to release the target decks to each of our component areas. So targets then would be cascaded to body, chassis, and powertrain. I'll try and quickly run through the last example here, which is the detail validation model using powertrain virtual inputs. So EDU source data sets will be generated by our powertrain colleagues, separated into gear forcing and e-machine forcing. So each mechanism is generated separately or using separate software. Within vehicle NVH, we generate 3D surfaces of mount rate, so high frequency rate versus axle torque. So we have a process to generate those. Airborne radiation from the EDUs then back calculated to and corrected using free field propagation corrections to volume velocity. And we will then run a separate build within OptiStruct to convert, using the EDU isolation assumptions, to convert the fundamental EDU displacements into body forcing. Then we have our processes of generating our ATFs. So ATFs to target within MATLAB, taken using a surrogate data set. In terms of body NTFs, our low frequencies is generated directly from Altair, and then we cross over with our adjusted high frequency NTFs, which similar to the ATFs are adjusted using a surrogate data set which is adjusted to target. And then we go to the final contribution build. So our airborne build happens, we run within MATLAB completely, and our structure-borne build is conducted within CA Auditioner. And then we make some additional adjustment for body ATF deltas in terms of our LDI within the mixer desk and the simulator model. And again, we have a free driver model at the end, run using Simulink. So finally, how do you set up the integration of the tool sets consistently within the department? The first area we spent a lot of time is improving the level of confidence that our leadership team have in the process. So that's primarily been improved through benchmarking. So we set up a process or a project where we built a simulation of one of our vehicles
and then we had exactly the same vehicle available to drive straight after the simulation experience. So that quickly provided a benchmark for the level of accuracy. But also making sure you've got an own vehicle always available to drive your target vehicles against, or your development vehicles against, is really key to maintaining the confidence. Overall correlation of the vehicle. So once you've gone through a development process, you eventually want to get the final test vehicle or your physical property available to drive against your development models. So that's pretty important. And then fundamentally, process repetition and time is necessary, as you would expect. Secondly, reducing the model build time. So as I say, when we started our source path observer models, it took 12 to 13 weeks to build, which is really not sustainable if you're having to wait that length of time through development processes. So we recently established an intra-departmental DOF-ID convention, so making sure that powertrain and chassis and body are all working off the same hymn sheet in terms of the numbering convention. Allows us to then stitch together the contributions quickly. That then links into the homogenized data sets. So again, where we mentioned having translation tools from target data sets, virtual data sets, and test. So we have established these toolkits in order to quickly convert the formats, which has sped up the process massively. So this, as I say, the external toolkit allows us to automate, so providing speed and consistency, removing human from the loop, and finally the Simulink integration. So again, removing the overheads from performance model builds, and finally optimizing your results for the correct forum. So we always try to build free driving models. It's the most immersive experience. However, if you have a lot more people that you want to demonstrate the vehicle performance to, then fixed driving models we would convert the free driving models into fixed driving models for specific load cases. And finally, we also have external processes to extract our high-level results against target, either used for issue identification or for formalized engineering validation. That's me. Thank you for listening.